We've talked about regular waves like water waves or sound waves diffracting, and since light is a wave, light is no different. So diffraction grating is often like a small set of openings, something that we could shine something like this, a laser through. And if we shined a laser through that diffraction grating on a screen, we would see that our laser diffracts. And what we would see on the screen is we would get tiny sections of brightness and dimness, and there would be pieces missing because not only is the light diffracting through that grating, but there's interference from all the different openings after that diffraction. So if we think about just a diffraction pattern, it's not going to look that different from other things we had diffracting. But as that diffracts through the opening, we also can think about it in terms of intensity. So there's going to be like an intense section in the very center, our central maximum, we're going to call it. And then we're going to notice sort of fading intensity of that light as we go out from each side of that, which makes sense if we think about the fact that light coming through an opening is going to be very bright as it passes straight through, but then as it spreads out, that intensity will vary. So we can almost think of that as like a frequency of how often does that intensity or light hit in those particular spots. So we have a large distribution in the center, and the distribution as that sort of goes further and further out, the light gets less and less intense the further we get from the center. If we have multiple openings, light's going to diffract through each opening and then interfere with itself. So if I draw a couple wavefronts here, I'm going to see that additionally, the other source also has wavefronts. And so those other wavefronts, we're going to start to see points of constructive and destructive interference, which is going to give us our diffraction pattern. So in this rough sketch, we can see that sort of in the center, I have my center maximum, my central maximum, and throughout that, I'm going to have other points of different amounts of interference, but in there I'll also get destructive interference. So I'm almost going to have like these big gaps of nothingness, not so much of a gradient as I saw with my other just diffraction pattern. And so again, I can sort of keep track of how often those things occur, with the central maximum being the place where it happens the most often, and these black lines I have being sort of the gaps where there's nothing due to destructive interference. So down the center, we have these points of constructive interference, which is why I have this big peak here, but I'm also going to have constructive interference at all these other points, which might lead us to one of these other peaks over here. At the same time, where I have destructive interference happening, I might have those locations. That's why in a location like that, I'm going to just have like nothing's making it to our sensor screen because it's being destructively interfered on the way. So as we lead all this towards quantifying it, we have a bunch of new variables that we have to identify. So this gap right here, D, is the distance between our openings. We have the angle at which our bright spots occur. That's going to be theta still. Theta is always an angle. L is the distance from the openings to the screen where we're detecting all these different bright spots. X is our distance between bright spots, and in this case, we'd measure from the central maximum. And then M is just like an integer number of bright spots away from the center. So the mathematical relationships we see here are a couple things. So D, the distance between the slits, times sine of theta is equal to M, the number of integers of bright spots that I see, times the wavelength. One thing we can do for that is we can use the sine of 90 degrees to measure basically one full side And that can tell us in total the number of bright spots on one side, because 90 degrees would cover everything on one half, everything to the side of the central maximum. The other mathematical relationship we see is similar, but it's a little bit different, including x, the distance between each bright spot, and L, the length from the openings to the screen or the detector screen. So that's m times wavelength over d is equal to x over L. All of this is on our reference tables, and we'll do some practice with how do we manipulate these situations for diffraction of light.